Okay, you're going to have to lock in for this one. This is something new, and it can be kind of a challenge, okay? So I'm going to try to go as slow as I can here and make sure that you see where things come from, but by the time we're done, this thing's going to be filled up with a lot of writing, so you may have to go back and forth through this and see if you can make sense of it. It also might help to write this down as you go. Just the act of writing it sometimes kind of sorts things out for you. So we're going to take a look in this video at what's called Hess's Law. And Hess's Law is basically kind of a creative way of using data that's already available to figure out how much energy change would happen in a certain reaction, even if we don't have that information available to us. We're going to use other reactions as building blocks to kind of make it up. Okay, now, what you have here, this is a target reaction we're looking at. And if we just take our mind away from writing things down for 1 second and say, what does this actually mean? This is hydrogen peroxide, liquid, like you have in your bathroom. If you crack the lid open and let it just sit out in the normal atmosphere, okay, eventually it's going to decompose into liquid water and oxygen gas is just going to float away, okay? And it's a decomposition reaction. Now, that reaction within it has a certain change in enthalpy, okay? There's an energy associated with this. We just don't have that information. What we do have are two other reactions given to us that have specific known amounts, but neither one of these reactions is exactly what we're looking for. It's kind of related, okay? This one is how you make water by putting hydrogen gas and oxygen gas together, big energy change, okay? And then this one is if we were to take pure hydrogen and pure oxygen gas to make hydrogen peroxide. If we did that reaction and got it to happen, it's got a little bit smaller energy change, but neither one of these is exactly what we're looking for. Here we're looking for hydrogen peroxide decomposing into water and oxygen gas. So what I'm going to try to do is I'm going to try to build this reaction with these two things by putting them together. Okay, now, I say put them together, it doesn't mean I put them together the way they are. So when you guys have done things in algebra like solving systems of equations, sometimes you set them up in a way where you might have to double one, you might have to flip one around and reverse it, you might have to make it negative instead of positive, and you try to do certain, you try to do certain operations to it where you don't change the meaning, but you change its formats to be helpful to you. Okay, we're going to do the same thing here. You'll kind of recognize this process, but it's just in a different application. So if I take a look at this situation, what I'm going to do is take these two given equations, and I'm going to try to build this. Okay, now the way I do that is I try to look for things that I know for sure I'm going to need. Okay, so I look at this, and this has three things involved in the reaction. Okay, now the first thing I'm going to notice is this right here, 2 moles of liquid water on the right side of the arrow as a product. I'm going to look for something like this. Okay, I want to find that in these reactions. And I find that right here. I have 2 moles of water, and it's on the right side of the arrow as a product. It's liquid. Everything seems to match. It's exactly the right amount. So what that tells me is I'm going to use this equation right here, and I'm going to make no changes to it whatsoever. Okay, so in order to obtain these 2 moles of water, I'm just going to write this equation down. I'm going to write 2H2 gas, and it's important you look at the states of matter here because they may be different, and they won't mean exactly the same thing. Something says gas and you're wanting a liquid, it's not representing the same amount of energy change. 2H2O liquid. Okay? Now, I just basically wrote this equation down here. All right? I just wrote it out and I didn't make any changes to it. So that means this energy value up here that's associated with it hasn't changed either. All right? So I'm going to say delta H for this reaction I just wrote down is negative 572 kilojoules. Okay, so I made no changes whatsoever, so I didn't make any changes to the energy amount either. Okay, now comes the trick, all right? Let's take a look at something else, all right? Let's go for this right here. Liquid hydrogen peroxide, H2O2. Where do I find that at? I find it over here. Now, what's different about this that I'm using compared to what I'm really looking for? There's two big differences. First of all, this is on the right side of the arrow, and I would like it to be on the left. Over here it's written as a product, over here it's written as a reactant. Okay, so I need this whole reaction reversed, okay, so that this will end up on the left just like I want it. The other difference is There's a 2 in front of it. Here there's only a 1. So I need to double it. Okay, so what I'm going to do is I'm going to put a 2 in front of it, but that means I have to put a 2 in front of everything else. I have to double all of the other amounts. It also means I have to double this. Okay, so there's 2 changes that happen. Number 1, I had to reverse this reaction. When I reversed that reaction, it went from being exothermic to endothermic. I'm going to change the negative to a positive. So if I flip the reaction around, it becomes positive. If it started out positive, it would become negative. We just change that sign. And then I had to double the amounts to make this a 2H2O2, just like I'm looking for up there. So I had to double the energy amount. Now let me write it the way I actually wanted it with those transformations. I'm going to put the 2H2O2 over on the left, 2H2O2, and that's liquid. Okay, that's the only thing on that side of the arrow. Okay, so now I'm going to draw the arrow. Remember, I've reversed this. I flipped it around. So on the other side, I have 2H2 gas, and I have 2O2 gas. And now I need to write the delta H value that would represent what I just put here, doubled and flipped. So I flip the sign and I double it, and this is going to end up being positive 376 kilojoules. So to reiterate, I wrote the first equation exactly the way it was because I didn't really need any changes to happen. I wrote the second equation flipped, reversed, okay, and doubled, and then I made sure that that energy amount reflected these changes that I produced over here. Now, if you've been able to kind of do this, you sort of have to look ahead and see where it's going. We should be able to add these 2 equations together. So let's see what happens when I do that. Okay? If I write out everything on the left of the arrow, so here's the arrow, here's the arrow. I'm going to write everything that's on the left as one side. Okay, so I have 2H2 gas plus O2 gas, that's these 2 things, and now this is also on the left, plus 2H2O2 liquid. Okay, so there's my 1, 2, 3 things that are on the left. I wrote them all out. Now comes my arrow. Now I got 3 things on the right. I've got 2H2 gas. I got 2H2O liquid and 2O2 gas. Okay. Now let's take a look at what we have here. Think of this as an equal sign like you would in mathematics, in algebra. If I have one thing on the left of the equal sign and one thing on the right of the equal sign, they're there, but they don't really need to be. They can cancel out. So I'm going to look at what cancels out. I've got 2 moles of hydrogen gas, 2 moles of hydrogen gas. They're on both sides, so I can basically eliminate them. What else do I have? Here I've got 1 mole of oxygen gas. Over here I've got 2 moles of oxygen gas. So I can get rid of one of those moles. 1O2 and 1O2 from each side are going to cancel out. And look what I'm left with. 2H2O2 decomposes into 2 waters and 1 oxygen gas molecule. I have the target reaction I was looking for. Now the whole purpose in that is if I made the right transformations along the way by adding these together, doubling this and flipping it around, as long as I did the same thing to the energy values, so they're reflective of what's really going on, then all I have to do is add those together. I can add those together and I get delta H for this reaction is negative 196 kilojoules. Okay, so I found out the enthalpy value, the heat transfer essentially in this reaction by building it from 2 other reactions that I already knew the heat values for. The trick is to look in your target equation you're trying to make and pick out some things that are very definitive and try to figure out where they are in your building blocks so that you know if you have to reverse something. Now you can basically flip any reaction and just flip the sign, and you can multiply any reaction by any number you want. Whole number, fraction, decimal, it doesn't matter. As long as you do it to the energy value, it's going to be true no matter what. Then we add them together, and if we get the overall reaction we're looking for, then that means adding the 2 enthalpy values will give us the enthalpy value for the reaction we're looking for also.